Hi everyone, it's great to see you all again. This is joint work with a bunch of people, primarily Manuel Ramos and Yahel, Eric. So, as Eric mentioned, when we actually started here, we didn't really treat power issue to give particular attention to, but in hindsight, it seems like it was one of the first obvious things that we had to do. So our experiences in rural power primarily come from some of our deployments. So I'm going to briefly talk about, just introduce some of those deployments where we got a lot of these experiences. So the first one is the Air Jaldi network, which Yahel has been involved with. It's a network in the city of Dharamshala, North India. Caters to a community of Tibetan exiles, and it typically has about 100 mesh routers and a few wild links. It's a mix of Linksys mesh routers and MikroTik routers for the wild links. And similarly, by now you're all familiar with the Arvind network. The main point to take away from this is that the wild routers that we use are similar to some of the wild routers we use with Air Jaldi, and the thing is that they tend to draw between 7 to 9 watts of power, and so that's the main thing to know. So looking at some of the data from Arvind in 2006 in the early stage of the deployment, I'm just looking at just the hardware faults, where you see the instances on the left, the description of the fault and the downtime. These are all this is kind of like hard won data where we found that things were not working. We actually had to go to the site to find out what was happening. So if you look at the first 4 faults, we see that 90% of the faults are power related, and we're, at least from this sample, represent 50% of the downtime. And these issues range from maybe simple outages, such as the router board was just not powered. Could be prolonged episodes of low voltages where the router was actually powered but was just hung. Could have been also due to surges, maybe because of poor grounding or lightning, where the router was now powered, but the data pins, these routers are powered by PoE, so the data pins were burnt out and so weren't actually connected to the network. Or again, due to low voltage, the router was on, but there was not enough power in total to support multiple wireless cards, high-powered wireless cards transmitting simultaneously. So, given that power was one of our main worry, it causes a lot of grief, we decided to study it in some amount of detail. So what we did essentially was we measured voltages in 2 South Indian villages for a period of 6 weeks, and the way we did this is we connected voltage probes from the grid into a power meter and just let it run for 6 weeks. So so we were expecting mostly outages, but as Eric mentioned, the data that came out was very surprising, frankly. So here the 2 colors represent the 2 villages, and you see on the left the voltage bins in which you measured the readings, and so the negative voltage bins don't really. What it means is essentially that the probes are connected in when the polarities were reversed. So what we see is that there were a lot of swells in the range of 300 to 500 volts, and normal voltage in India is 220 to 240 volts. And we also see, and these swells of 300 to 500 volts would last on the order of milliseconds. And we also saw spikes as high as 1000 volts, which lasted microseconds. And it actually explained quite a bit of what we were doing. I mean, a lot of these swells and spikes cause us to lose a lot of equipment on the field. For example, at Air Jaldi, I mean, it's been estimated that 50 power adapters, just because of these spikes, had about 30 power over Ethernet ports burned because of these surges. What is not shown in this graph is also our issues or the problems we faced because of low voltages, typically seen when you're far away from the transformer or just after a power outage when the power is coming back on. There are periods of low voltage. So as the router boots up, during low voltage, it kind of gets stuck and just it hangs. And typically there's a mechanism to sort of recover, and there's a hardware watchdog that is also on the router, and if it doesn't get a message from the kernel, then it tries to reboot the router. But since the watchdog is also on the same board as the router, it suffers from the same low voltage problem, and it's just stuck itself. And so the hardware watchdog also fails. The other thing we saw were frequent fluctuations, especially during periods of low voltages, but in general also. So what happens now is in periods of low voltage, there's frequent fluctuations. There are transient instances of reaching sort of 0 volts, and so the router unnecessarily reboots automatically multiple times. And with each boot, there's stuff written onto the compact flash card, and with increasing writes, the corruption or failing of the CF card increases as well. Also, if you have a battery system and you're actually using that and you're using power from the grid to charge the battery, then the frequent fluctuations also don't really charge the battery well. In fact, could possibly also damage the chemistry of the battery such that it accelerates its degradation. And all issues we have faced, and my guess is that a lot of people in the audience also have faced these issues. Understanding this was the biggest challenge. This is why is this happening? So the obvious question would be, what about UPS? I mean, you can use UPS. Affordable UPSs are about on the order of $100 to $300 systems are of the standby type. So the primary source of power is actually grid power. Battery power, stable battery power, is only supplied when there's no grid power. Best power when there was no grid power from the battery. And all the instances that I showed from the 2006 hardware fault episodes actually did use these UPSs. So despite that, we had a lot of these problems. So here, just want to sort of take a step back, and this is something we realized, maybe about a year ago, as to what is the real cost of power. So now, since these routers, in this particular case, they draw 7 watts of power, assuming continuous draw for a whole month, using electricity rates in India, if you just pay grid cost for that, that would cost 25 cents. But because the power is so bad and causes a lot of downtime, so you have to clean it. Say, for example, using UPS and battery. But then, if you spend for UPS and battery and adjusting for the lifetime of this equipment, it turns out that now we're paying $6 a month, which is about 24 times, 25 times higher than what you could pay for the grid. So it's a lot more. The other thing to note that is, okay, so suppose we use a small solar setup. It turns out that that is kind of comparable to what we would do with UPS and battery. It's not that much more expensive. And it gives us the advantage of actually powering up in remote locations. So with these things in mind, some of the directions we took ranged between creating support for low voltage disconnects and also a low cost solar power controller, now that we were comfortable with the fact that this was comparable to UPSs and batteries. So low voltage disconnect. Essentially, it's a circuit that disconnects the load when the voltage is low, typically found in battery chargers, so that when the battery's voltage drops, then it prevents the battery, it disconnects the load, so it prevents the battery from over discharging. As a good side effect, it also prevents the load, say in this case a router, from being powered on during low voltage situations as well, and thus prevents hanging. So in fact, without low voltage disconnects, at some point at Air Jaldi, things would just hang, and there would be no other way but to manually visit the site, physically visit the site, and reboot it. And at some point, there was a dedicated team at Air Jaldi, just basically, which was their job, just to go around and just flip switches and reboot routers. There are off-the-shelf LVDs, but they tend to be very sensitive to the actual low voltage threshold, and as a result, they tend to oscillate a lot. And this, in fact, increases our automatic reboot problem, which then increases our compact flash card problems as well. So Understanding this took some time, but this is actually pretty simple, and all you have to do is design just a new circuit with just better delay, and that resulted in absolutely no more manual visits or reboots, and this is on the order of 50 cents, and you can just get the design from AirJolly actually on their website as well. So just 50 cents. But low voltages are not the only problem. This is a picture of the low power controller that we saw in an earlier talk today. We have to deal with swells, transient spikes, and we'd also like to enable power at remote sites as well. So for that, we developed a microcontroller-based power controller that basically interfaces the panels to the batteries and controls how much power is extracted from the panel, and also controls how well the battery is also charged. So some of the features that we have in this. Number one is peak power tracking, which what it does is all these panels, they operate at a certain current voltage conditions depending on environmental characteristics, and so if we can fix it such that fix the operating point such that we can draw maximum power at that point, then we've been able to show for about a year of testing that we can draw 15% more power, which is actually significant during cloudy conditions as well. Then it also has low voltage disconnect and also trickle charging, which basically means that once the battery has reached its maximum charge, then the charge is trickled to it, and both these combined actually can help double the battery life, which in many cases means just extending the battery life to its rated capacity, because in a lot of these places batteries die in 6 months or 1 month or 1 year, even though they're rated for 2 years because of the poor grid. We take care of most spikes and swells through voltage regulators. The other thing you notice particularly useful for wireless networks is the power over Ethernet port over there. So it uses this to actually power the router as well. But now, since we can send data to it as well, we can actually remotely manage the router as well, which is actually a big win. So to put this together, it costs us about $70. We haven't actually used this in any of our production networks at Arvind, but we have tested it in the Philippines for about a year, close to a year now, and for 2 schools, and we haven't had any reports of any issues with the routers there using this. At several stages of development, we did have a few issues. So I just wanted to close by just giving you some operational results. I mean, the main thing is that understanding a lot of these problems took a lot of time, but the good news is that the fixes, once it was understood what had to be done, were pretty simple. So here, I'm just going to talk about on the x-axis the different kinds of power-related faults and the counts, and the blue represents sort of before the power intervention was applied and after. So for example, at AirJolly, once low voltage disconnect was done correctly, we were able to completely eliminate the need for manual physical visits for manual reboots, and also the issue of automatic reboots. Then at Arvind, if you just look at the total number of power related issues in 2007, we were able to decrease them from 16 to 4. Just by using simple low voltage disconnect, and also a combination of UPS as well, and that actually helped with the prolonged downtimes, where we stopped downtimes for greater than a day. And another thing is that because of the simple low voltage disconnect, we were able to completely eliminate CF card corruptions as well at Arvind. Now going forward, we're looking at since we have a solar charge controller that actually does a bunch of the cleaning, the next step is to see if we can actually provide grid power as input to it, and then get that power cleaning, hopefully for free. And so then we can use that system as some kind of, say, a UPS power controller kind of combo for roughly the same price. But that's something we're working on, and I'd actually invite people. It's an open source project, and I'd like to invite people to work on it with us, help us, and maybe even take parts of the design as well. So with that, I'd like to close, and our website, including details about the power project, are there. I'm happy to take questions.
could go back one slide. How many units does this represent?
So if you look at, so they're data points from two networks. So if you look at the Air Jaldi network, which is the first bar over there, it represents on the order of about 100 routers. Is that right, Jahil?
A little bit more.
A little bit more, okay. And if you look at Arvind, it's a smaller network. So you're looking at about maybe 15 routers or something like that.
So 115 units over 12 months?
Yes.
Okay.
Yeah.
Other questions?
Question, Louis?
Done.